Hi, today we are going to see about frequency response analysis in control system engineering. The outline of this video is review about previous classes and what is frequency response and its frequency domain specifications, resonant peak, activity, resonant frequency, bandwidth. What is frequency response? The response of a system can be partitioned into both the transient response and the steady state response. We can find the transient response by using Fourier integral. The steady state response of a system for an input sinusoidal signal is known as the frequency response. It will focus only on the steady state response. If a sinusoidal signal is applied as an input to a linear time invariant system, then it produces the steady state output, which is also a sinusoidal signal. The input and output sinusoidal signals have the same frequency but different amplitude and phase angles. The input signal be A sin of omega naught t and the open loop transfer function will be g of s. We can represent g of j omega in terms of magnitude and phase as shown below. G of j omega equal to modulus of g of j omega angle of g of j omega. The output signal is c of t, which is equal to a modulus of g of j omega naught sin of omega naught t plus angle g of j omega naught. A short introduction to the steady state response of control system to sinusoidal inputs will be given. Frequency domain specifications for a control system will be examined. Bode plot and their construction using asymptotic approximations will be presented. In frequency response analysis of control systems, the steady state response of the system to sinusoidal input is of interest. The frequency response analysis are carried out in the frequency domain rather than the time domain. It is to be noted that time domain properties of a control system can be predicted from its frequency domain characteristics. To carry out the same process in the frequency domain for sinusoidal steady state analysis, once replace the Laplace variable s with j omega. In the input output relation, C of s equal to T of s R of s, with the result C of j omega equal to T of j omega R of j omega. For the input and output described by R of t or sin omega t, C of t equal to C sin omega t plus psi. The amplitude and the phase of the output can be written as C equal to R t of j omega and psi equal to angle of t j omega. Remember that for a complex number we expressed in its real and imaginary parts. Z equal to a plus bj. The magnitude is given by z equal to a square plus b square and the phase is given by angle z equal to tan inverse of b. For a system described by the differential equation x plus 2x equal to y of t, then determine the steady state response for a pure sine wave y of t equal to 3 sine of 0.5 t. The transfer function is given by t of s equal to x of s divided by y of s, which is equal to 1 divided by s into s plus t. The solutions for this example 2 is given in this slide. The amplitude of the output sinusoidal signal is obtained by multiplying the amplitude of the input sinusoidal signal and the magnitude of g of j omega at omega equal to omega naught. The phase of the output sinusoidal signal is obtained by adding the phase of the input signal and the phase g of j omega at omega equal to omega naught, where a is the amplitude of the input signal, omega naught is the angular frequency of the input sinusoidal signal. We can write angular frequency omega naught as shown below. Omega naught equal to 2 pi f naught. Here f naught is the frequency of the input sinusoidal signal. Similarly, you can follow the same procedure for closed loop control system. The resonant peak, resonant frequency and bandwidth. Consider the transfer function of the second order closed loop control system as T of s equal to C of s divided by R of s, which is equal to omega n square divided by s square plus 2 dou omega ns plus omega n square. By substituting s equal to j omega in the above equation, we can get these solutions as shown in this slide. The magnitude and phase of T of j omega is given in this slide. It is the frequency at which the magnitude of the frequency response has peak value for the first time. It is denoted by omega r. At omega equal to omega r, the first derivative of the magnitude of T of j omega is 0. Differentiating m with respect to u, we get the solution u equal to square root of 1 minus 2 dou square, and omega r equal to omega n square root of 1 minus 2 dou square. Resonant peak, it is the peak value of the magnitude of T of j omega. It is denoted by mr. Resonant peak in frequency response corresponding to the peak overshoot in the time domain transient response for certain values of damping ratio dou. So the resonant peak and peak overshoot are correlated to each other. The magnitude of T of j omega is given as mr equal to 1 divided by 2 del square root of 1 minus 2 del square. Bandwidth, it is the range of frequencies over which the magnitude of T of j omega drops to 70.7% from its zero frequency value. At omega equal to 0, the value of u will be 0. Substitute u equal to 0 in m, and then we get the solution as omega b equal to omega n into square root of 1 minus 2 dou square plus square root of 2 minus 4 dou square plus 4 dou power 4. Bandwidth omega b in the frequency response is inversely proportional to the rise time Tr in the time domain transient response. Thank you.